Moon tune enabled. Go ahead, Kauai. Okay, go
You're ready to start, you bastard.
on.
Dude, that is the most funniest product I've ever seen in my life.
25% ether. We only want a quarter of a bomb. Don't worry.
So I wonder how this racks up against regular old carb cleaner or brake cleaner.
Well, the non, whatever they call these days stuff, it's not what it used to be, put it that way.
I have fond memories of being a kid and setting wasp's nest on fire with carb cleaner.
That sounds good. All right. Well,
That's a funny story for a later time. Okay, we're back.
starting the engine. What to
Yeah, man.
expect? Hot, cold starting, idle control, basic correction tables, volumetric efficiency tuning, cranking, fueling, ignition basics, general tuning tips. That's going to be what we're covering in this video. Claudia's going to kick us off to what to expect.
Okay, well, you've wired up all your injectors. You've got a proper fuel system in there. You've checked for leaks. You promised to check for leaks so that you don't have any incidents happening. Obviously, you turn on your fuel pump. You make sure there's no leaks anywhere in the system. Your rails are tight. Your lines are tight. Your regulator is well done. And you've got your proper base pressure. We recommend 50, 43 and a half. One of the things that dictates where you put this base pressure is the maximum amount of boost that you will run, or in the case of having an aspirated engine, where do you really think your injectors will like it? And are they low flow rate or high flow rate? How much do you need to atomize the fuel?
We should definitely talk about, I did mention this very, very briefly when I brought up that Inject Dynamics Excel spreadsheet.
Mhm.
Our nominal pressure is what we're referring to, is we can either have the vacuum line off, engine on, that's our nominal pressure at the regulator with a fuel pressure sensor. And when you have, let's say, a bunch of forged 90-degree fittings that add resistance to that pump going up, those are restrictions to the lines. When you go and you have boost pressure, that is going to be adding to that nominal number. And the total is what you will see from the fuel pump itself. We don't have a fuel pressure sensor at the fuel pump, so we don't know what it's actually seeing, but we can assume that we have line losses based on each fitting used, based on fuel line sizing, and based on our pressure. And so you can calculate it out kind of like what I was showing you, where we had a 6,900 cc per minute fuel pump, um, and four injectors that I just pull off the top of my head, the 1300s, whatever it was, at that same pressure. And it gave us a 15% overhead. Well, of that 15%, you also have line losses that we don't know exact values of, and those need to be thought of. When you have a larger line, you have less restriction. So you can't go too big of a line. It's always just going to be a proportionally less restrictive configuration. So
Actually, that's a good word. The everything in a vehicle has to be proportionate. You can't ask for a 1.1 AFR back housing turbo to run 500 horsepower worth of nitrous, but then you don't put the nitrous in. So everything in the engine is proportional. How much injector you need based on the horsepower capability of the motor, and that will dictate how much fuel volume you will need to feed all the power. So going into the settings and the combination of sensors and components, all that has to be taken into account so that your power output is good. You don't have any surprises when it comes to, let's say, the engine won't perform past a certain point because there's either an exhaust restriction or the fuel system just doesn't cut it, or the injectors quite simply are not big enough. And eventually you run into a wall where something is just preventing you from continuing because it becomes the restriction. So keep that in mind. The whole vehicle has to be balanced,
We
not
call
just the chassis.
right. So we call this synergy, right? It's something in which the individual components can somehow add up to become a better version or better combination than just their individual values. This is always where
The
we try to attain from our tuning. That's
the
why I call it
sum of the
calibration.
parts the sum of the parts is better than the individual parts on their own.
Right, by
Yeah.
themselves.
Yeah. So what to expect effectively is, when you set your goals, you have to obviously make the assumptions that are necessary to fulfill those goals. So the first thing you probably want to go into, I don't know if you want to bring up a table or some fuel settings. Obviously, the
Um,
number of injectors, your fuel volume, the capacity of the motor, how you wire them up. Should we?
we'll do a quick and dirty. So I'll
Okay.
show, for instance, the main
So
things we're looking for. So when we go to start an engine, we're going to have our coolant correction based on our temperature, and we're going to have a post-start additional correction. So right when we go to start the engine, to stabilize that engine, the coolant temperature might be whatever outside is. Let's say it's 32 degrees Fahrenheit. And to make a correct value when the car is at that temperature, it's going to need a specific amount of fuel more than standard to maintain smoothness of the engine and help with the warm-up procedure. Um, Engines consume more air when cold than they do hot, which is why if you see an idle, it'll go up because it needs uh, less energy in forms of fuel when the engine is warm. So that same air mass that it had at the throttle body is not going to be enough when the engine is cold, and we're going to compensate with that with more fueling. Uh, so let me just
yeah,
show.
so I've got here my software on the screen, and obviously
Yeah,
we
so
have
go to the coolant
some
temp
correction.
first. Yeah.
That coolant temp, you got your coolant temp, which is basically the colder the engine, the more fuel it'll need, and the reason for this is because you get pooling of the fuel or vapor or condensation of the fuel rather in the walls of the manifold. So fuel is wasted that way. It's not really burned when it's turned back into a liquid. So you need more fuel to compensate for that. Besides
Post
that, you
Go to
also
the
have
post start correction, which is the post start is going to be if the engine you go to crank it, it starts initially very well and then immediately dies. It's likely going to need a little bit more post start to get it settled because you could have it where it starts and you hold the throttle slightly and then it maintains after a 30-second period. That's when it's going back to our coolant temp correction overall. But the coolant temp is still going to be there. The post start is an additional help to that to make sure that we are stabilized when cold. This is what gives us a lot of that warm up procedure, consistency, drivability sort of thing. Um, Kind of blending these to always be accurate. We can also make a
um,
compensation on our lambda correction. So if we go right below right there, there's a lambda correction. No, right above that. Oh, right above
oh,
that,
you
lambda
want these guys?
correction and coolant temp correction. So when we have a coolant temp that is lower than our operating temperature, we could say, well, I want you to take our target lambda and offset it by this amount to make the engine smoother, safer, whatever we want to do for that particular engine configuration. So we do the same thing on the hot side. When the engine starts to overheat, now we take our target lambda and we're going to offset by that given amount. Now, Claudia is going to go over prime pulse, what that means, and the
Yeah.
actual fuel start.
Actually, I mistakenly pulled an old firmware map, but anyway, the point is the same.
Yeah.
We could talk about it too. So the prime pulse is an initial burst of fuel that the ECU will do specifically when you first kick on the starter and you start to get RPMs. This is going to happen below our cranking RPM threshold that we set for the starter. So on a newer firmware, which unfortunately I grabbed an old one, we also have cranking fuel.
Well, that'll
So
be under
before,
our fuel tuning. You just have it deselected. Just click the fuel tuning
yeah,
tab.
oh, the hit, yeah. So yeah, I can turn the cranking on there. So
There it is.
effectively, we can also have cranking fuel, which will happen exclusively during the cranking phase or the first RPM that the ECU is seeing below the threshold we set before. Now, between the prime pulse and the cranking, the engine should be able to fire up, have enough fuel to fire up. And then after it's running, of course, it'll go off of the post start and the coolant. Now, the post start is usually done on the engine's temperature and time. So this goes away after a certain time. Normally between 0 and 30 seconds should be nice. You should also correlate this to the idle control. You
Yes.
know how you get the engine to fast idle a little bit when it's cold to help with idle RPMs at those temperatures. This is the fuel that helps to maintain it. So remember, if you crank on the engine and it goes wham to about 1500 RPMs and immediately just shuts off, you don't have enough fuel to keep it going.
Yeah, we're using this as a smoothing factor for the overall engine's needs. We're trying to stabilize the engine to where it is now moving in a smooth manner without throwing a bunch of ignition timing or a bunch of idle air at it. The fueling
Yeah.
is part of that equation to make it
Yeah.
smooth.
So on another set of values that we talked before, which were the injection dead time and the flow rate, and these are based off of injector pressure differential. Now, the reason you want to have it based off of injector pressure differential is because that way you are going off of the rating of the injector, and the ECU can compensate looking at both fuel pressure itself and the amount of boost or load that you're generating. That way, the computer can say, well, okay, well, this much boost pressure is hitting the injector tip, so it's going to be trying to stop fuel from coming out of the injector. I've got to compensate for that, and that's where the injector pressure differential combined with the voltage, combined with the flow rate, will let the ECU pulse the injector to where it's not restricted by the pressure boost trying to keep it from going into the motor.
So when we go to crank, I'll just go over the prime pulse one more time real quick. So we've got the initial prime pulse, which is a big burst of fuel. And then if you're holding that starter after that initial, let's say 1 second or so, then it starts to use that cranking table. So if it goes to try to start and then it doesn't start after that long duration, that usually means that the prime pulse can be added to, or the cranking can be added or subtracted to depending on what it needs. So the first thing I would do is I would say, okay, let's go add 15 more percent to our prime pulse and see what happens with this. And then we're going to also reduce our cranking because it might have too much cranking fuel that's causing it to continue to roll over and not catch. So I would give it a larger prime pulse because it helped it get up and then pull away the cranking to bring it back to actually catch on the motor. With this in particular, we also have ignition timing that might be an ideal situation for during cranking. We might want to target a specific cranking ignition angle. Well, if we think of very high compression engines, when you have a high cylinder pressure from a more advanced timing, that's going to make it a much more difficult to start engine. So many a times we'll find that the cranking timing to be retarded by comparison to the rest of the map will actually help start the engine earlier and easier. So some engines might want 15 degrees BTDC, which is very rare. Most will be closer to, in this rotary application that Claudio showed, 8 degrees BTDC to 5 degrees ATDC. And that's going to be a much easier to spin, less cylinder pressure ignition to start the engine for cranking.
And then, of course, cranking timing is highly dependent on temperature as well, just like everything else. A hot engine will probably want more timing because now the cylinder pressures are different and the temperature is higher, so the fuel can catch a lot earlier.
Yep.
All right. So cold engine needs more fuel. A hot engine tends to need less fuel. A cold engine needs less timing. A hot engine can probably use more timing. So it's all proportional.
I would say that the cold engine needs more air to have the same idle RPM. So that's
It's actually more fuel
it
on a
is.
cold
It
engine.
is it is more fuel, but it also
But
needs more air, which is why your throttle body position can maintain what it is. And when you go to start it, the engine might idle at 800 RPM without idle air control valve, and then when it's warm, it might be 1100 RPM. So that's why I'm saying the consuming air that the engine needs to be required to run will be more air is necessary, which is why we use idle air control valves or drive-by wires to control an additional air mass into the engine when the engine is cold. That's what makes it stable when hot. So we want to set our throttle body positioning to where the engine operates where we want it to when hot, to where it only maybe has 15 to 20% on idle control, which should always be closed on boost if we have a standard two-wire BAC. And then we would have the additional idle control added when the engine is cold. And then we also give it an additional RPM target for that idle to help with the warm-up procedure to be a little bit faster. And then we can also change, of course, the fueling, the targets for the fueling when that is a cold engine, giving it a little richer mixture will make it more stable, and it will help again with the warmer procedure being faster.
All right. You want to talk a little bit about idle control, or do we leave idle control for the
No, that should be on this one as well.
later?
We're going to talk about idle control.
Okay.
So,
So idle control, it's part of your cold start, hot start, help the engine stay at a stable RPM, and it's basically dependent on the type of valve that you have, which will be two-wire valves or solenoids, or it's a solenoid, a semi injector. Just it's a coil inside that with a magnet that needs a pulse. Then you have the three-wire valves, which are also solenoids but require a pulse not only to open but also to close. And then you've got 4 and 6 wire stepper motors, which are basically valves that move in two directions and require a coil current to be fed from one side or the other to reverse the direction. The difference between a 4-wire and a 6-wire valve is that the 6-wire valves have a power wire to feed the coils, whereas in the 4-wire ones, the ECU is doing the power management through the 4 wires instead. An example of a 6-wire is a 2J or a 4G63 Mitsubishi. And normally, if the wiring has the power wires, there are some settings in the idle control outputs that you need to disable or turn to low current. And if it's not powered, then you want to turn on those settings to the high current option of the stepper motor outputs. Those would be the green wires.
So let's talk about more so the frequency of these will be dependent on the model. You'll
Yes,
hear something to where if it is buzzing to something
yes,
that you don't like the frequency of, these are generally okay giving a different range. Okay. The
yeah.
faster that frequency, the narrower the total control range will be. However, it'll be quieter. And sometimes it runs cooler or hotter depending on how you're doing this. So for RX-7s, for instance, their factory is 244 hertz. I run them out to about 500 hertz when needed, but normally they stay pretty quiet.
Yeah.
We have our closed loop controls here. This car actually had an idle control drop issue to where for whatever reason, the amount of airflow given from the throttle body was inadequate as our base. So normally, I said earlier, about 15 to 20% or something of idle control, and then the rest of it being on the throttle body when warm. This car obviously needed more than that, which is why we have an additional decel offset here that's quite high, an additional max speed offset that's quite high because this car was dipping more so coming down off of a hard acceleration into an idle condition. And then our stall offset here, this is in the scenario that the RPM in this case dips 400 RPM below our target, it will maximize the idle control output to 100%. To really get this stable on most vehicles, you're going to want to use both P and I, proportional and integral.
Yeah.
Most Haltech base maps in this scenario will have only integral.
Yep.
They don't have a differential, and then they'll run an ignition table to offset. So you have ignition catching the engine, and you'll have air catching the engine. Now, while that is one way to do it, if you have a zero demand ignition table, then that will be less likely what you want to do because you're going to have ignition adding on top of ignition. So you'll end up having, let's say you gave it a ghost cam sort of thing where you're going 18 degrees to -5 degrees within a 50 RPM period, and the engine's brapping and it's nice, beautiful brap. Well, by adding an additional idle control ignition, you're going to be pulling away from that. And you could be overheating the engine by running too much retard of the ignition. Or you can do a little bit too aggressive and it's overshooting its targets and now fighting the PID of the idle control by running too much ignition. So we do a little bit of P here and get rid of the ignition to now stabilize that situation. So now it'll catch it with the P, and the integral is it's going to be its control for idle control. And then you'll see stuff like our targets can change based on engine temperature. And then our closed loop table should be a decent gradient. On this one here, I turn off idle control when the engine's off. I just find it's nice to do a very simple table like this. Or you can add a condition, do the same thing. That way it's not buzzing when you have the key on. Simple as that.
Yeah, usually for the idle valves, for figuring out the frequency, it's as simple as just typing in a number, let's say usually 100, 140 hertz. You will hear it either have a low-pitched rattle or a high-pitched hum. And the higher, just go gradually higher and higher, and then you'll be able to clear out that hum, and it's just be quiet, and it'll work just fine. It's not going to really hurt it.
Back.
All right, another outage. Anyway,
hey man,
so
that 4K camera. Look at that beautiful gradient going on here. Camera's doing a good job.
Yeah. So idle control. Figure out what you have. It's not that hard to figure the frequencies out for the 2 and 3 wire valves. For the steppers, most of the popular ones that are left in the world are the 2JZs, the 4G63s, specifically the Subaru 99 to 2000 and WRXs, and then of course the GM old style 4-plug square or the GM newer style 4-plug in a row. Most of these valves, there's a base map somewhere in the Haltech folder that can help you get started, and on other brands as well. If not, there's actually documentation that it kind of gives you some rough settings to go off of. So a little homework goes a long way in figuring how to set these up.
But I think for the most part, that covers what to expect for basic corrections for volumetric efficiency tuning.
Idle control,
Cranking
getting the
fueling.
engine. getting the engine to hold a nice steady idle while you check everything else or start configuring the rest of your sensors and so on and so forth.
So we should talk about what is volumetric efficiency,
Definitely.
where to offset injector data if needed to get proper VE numbers in a real world modeling. Um, all of these are really kind of an estimation. This is, we're using the best data we can get, as much of it as we can get, and then we're trying to estimate it to be as accurate as possible and repeatable. And then the repeatability is where we're getting our both performance and our safety margin. When it's not repeatable, we can't push a car as hard, and therefore we have to detune more. So that's why it's very important to understand volumetric efficiency is a cylinder filling in a percentage of efficiency. Okay, that's the easiest, quick and dirty way of saying it. So Claudia, if you want to pull up a map of on your end what you
Yeah.
think
So
is a good looking volumetric efficiency curve for a specific application, and something that makes sense.
so this is just a little bit of a tune here for a 13B. It's got nothing fancy. There are a few humps here and there, but that's just because of specific engine needs and the specifics of where this vehicle is located, what the fuel is using, the drivability. Most of the little quirks there are because of that's where the engine sits the most, so that's where the car will probably be correcting the most. But the key
And
point here is, yeah,
so when you have this is a car with two-stage injection here. So
yeah,
that
of course, this is a
whole
rotary.
back end of this. So if we were to go look at this back end when it's under high load over here, the reason why it's
Where did,
flattening lower is because that injector is flowing more than what was expected in the fuel model. So it goes from this nice shape upward and then it rolls away. And the reason it's rolling away is because the secondary injectors are flowing more than what was initially inspected of them or expected of them. So that's why if you look at it that way, you've got this big curve coming up and then it falls down off this mountain and then the secondaries are kind of curved this way. They're beautifully shaped, but they're flowing more than expected. If the injector flows less than expected, the mapping will go the opposite direction, now going past the peak of the mountain of the primary injector.
so another way of looking at it is we could say a V curve tends to follow the torque curve of the motor. So the higher the peak torque, or the closer you are to peak torque, the more fuel the engine's going to need. And as you start going away from that peak torque, the less fuel the engine's going to need. So that's why you usually get a taper going downwards past there. Now, on a more efficient engine with a better tuning, with a proper exhaust or a bigger exhaust or a bigger turbo, you're probably going to see that the power kind of tends to stay on a even direction all the time, or tends to stay even all the way through the rev limiter.
Yeah, I'll pull it up as well just to kind of show another example. Let me see if I can grab one real quick.
So while you look for it, basically the way to think about volumetric efficiency is this. The engine moves air from one side to the other. This amount of air needs to be fed an amount of fuel to be able to produce the power you need. And then that is what your system is taking into account. The engine volume, the number of injectors, the size of the injectors, what mixture you want to run, the temperatures of the engine and the airflow. This is dictating in air density. All these variables get combined into one formula in order to calculate the right amount of fuel for the air the engine is moving. Now, the air obviously is measured either by a flow meter or by a map sensor in the case of speed density. And then this information combined with your throttle opening and your other sensors let the ECU calculate all that. Now, theoretically, this table will let you know 9 times out of 10 if there's a problem. If as you gain experience, most engines will tend to have a specific slope or shape to the curve. if you start needing to take numbers down further than you're used to or up further than you're used to on a typical application, that'll probably give you a good indication that there's something out of place, whether you don't have the right information on an injector, or the fuel pressure is not correct to what you think it is, or the engine simply isn't the volume or doesn't have the compression that you think it should have.
So this is an interesting one right here. This is actually a
What,
car that was modeled the other
what
day.
what's this
And
one?
this is a three-stage 13B. And what's
Ah,
interesting about this one is because the Bridgeport carried far more airflow than what is normally expected, our peak torque is actually flat and it's through a huge region.
yeah,
So
I see
we
that.
have a very, very large peak torque. And for every tuner, we're going to do something a little bit different when we come to our target lambda. So some people will have a richer target lambda based on rotational speed of the engine because you want to have additional cooling there. So that could make this where it should be rolling off pretty heavily. Instead of that, it's actually rolling off softly because our targets have changed for that position. So what's cool is when we work with multiple injectors, when you have the injectors proper, we'll do that. When we don't, let's say we have the secondaries here, it'll look something like this. This is very exaggerated, of course, but this would show that the secondary injectors are flowing, let's say in this case, 15% more fuel than what we expected. So the VE will drop down into this. And what you can do to compensate is you can go into our secondary fueling here, and you can say that our injector data is now take this compensation and go, boop. All right, try it out. See what happens. Did you now get that V curve to now flatten back out to look like that?
I would do that in the flow rate before I would do it in the dead
Yes,
times.
yes, of course. But point being that you can adjust your injector either dead time or flow rate to match what should be the corrected VE for that engine. So in the scenario that you see something that is looking like this, you should take a look at either your dead time or flow rate and compensate accordingly to make it what is a better, closer modeled VE.
Yeah, so I've seen it happen where guys tell you, "Oh, I have a 1,000 cc injector," and you're tuning, and then all of a sudden you start looking at the wideband, and the
you don't
wideband is
have a thousand
saying,
cc.
"No, no," the wideband is saying, "Well, okay, your fuel AFRs are right now at 9.8 gasoline AFR." It says, "Okay, it's a tad rich." So you
Yeah,
start knocking 30% fuel, less fuel on it. So you're assuming, well, if I have to take out 30% fuel to get it to idle properly at 13, then, well, my injector's definitely not 1,000 cc. It is way, way bigger. So then, of course, if the reverse is happening, if I have to go, usually an average idle V would be about 55, 60. If I have to go 75 at idle, well, then my injector is definitely not 1,000 cc. It's probably smaller.
that's right.
So these are indicators, and then my fuel pressure is fine. So these are subtle indicators that are pointing you in the direction of say, hey, there's a problem here. There's a variable that is out of place, and you're not really considering it.
That's right. And so I think what we tried to explain in this video was as a calibrator, it's not just slamming numbers into something to make it work. That's not right. You need to figure out why you're offsetting certain things to make things consistent. And our jobs are to make these engines run consistently, so therefore we can push them further. The reason why there have been such big power advances in the last 10 years for all sorts of motorsport is because the consistency of the power output is allowing us to find limitations slowly. And because we're finding them slowly, we're finding mechanical limitations, which is amazing. Because you're either going to be fuel limited, whether you're detonation or whatever it is, or you're going to be ignition limited, or you're going to be mechanical limited. So ideally, with an ignition 1A, that's going to be your limitation, your ignition limited. You're not running out of fuel, the engine's strong, right? That's pretty cool. When you are fuel limited, you have enough ignition, enough actual engine strength, that's fine too. Upsize injectors, and then you find the next weak link. But you never want to really run up on an engine with strength limitations without having adequate fuel and ignition. And the way to do that is to, again, slowly creep up on these limitations and say, hey, we should upgrade to our ignition system to a CDI because we've now reached this point of inconsistent, let's say, high RPM misfires due to ignition blowing out. Yeah.
On a side note, we can probably say the IG1As so far they're pretty reliable to the tune of about 650.
Yep. 650, 800 RPM or 850 RPM. Just kidding.
You mean 9,000 RPM? 9,000 RPM or 10?
I would keep ignition 1As under 8,500 RPM and under 25 pounds of boost for most setups.
34.
I've done 38 on a few of them, but it's a matter of, do you want the safety? I like the safety net and consistency.
Turn on engine protection. Yeah.
Always.
Well,
You have
yeah,
them,
so,
use all of them.
yeah, definitely. So I think that covers about as much fueling as we need, unless we need to get geeky and technical.
Nah, I think that's going to do more than most have ever seen online in any form. And what we're providing, I think, is enough high bar mixed with fundamentals that people will get it. I think we're good to go there.
I always say this: play with the software, click everything there is to click. I mean, if you can't find a setting, obviously somebody can point you in the right direction. So here it is. Now, what are the min, max, or average values you should do? Then you need to speak to the tuner and get down with them and try to learn a little more. There are other alternatives, but obviously we try to make this as simple and as effective as possible for everybody.
And the main thing is if you guys need professional tuning, reach out to one of us. It's that simple. We'll take care of you.
We're available via email and phone and web and forums and Facebook. All right, everybody. We'll see you on the next one.
Cheers, y'all.
All right.